Okay, I wanted to briefly discuss these questions at the end of 10F. They're not going to be tested. So from 11 onwards, 11, where it says know Pascal's triangle and write out Pascal's triangle, that could be tested. But when we get to 11D onwards, I'm almost certain that you won't have to do that style of question on a test. But I think there's probably some of you wondering what's going on here. So I'm going to briefly look at 13 because that's the hard one, but to give you a hint on how to do 11D, what you can do to get your 2 to the n here, 2 to the n. Well, how can I get it from this expansion? I could say x equals 1. So 1 plus 1 to the power of n is 2 to the n. And if I come through here and make all of these x's 1s, then the question should fall out from that. Okay? Similarly, how can I get this 0? Right? When we get to question 12, I could do it in exactly the same way. So I could, well, not exactly, but using the same setup. This 1 plus x to the n, how can I make that equal 0? I could make the x, we could let your x equal a minus 1. Right? So you'll be saying 1 minus 1 to the power of n. You could expand that out in the same way as they've done here and here. You'll find that you start getting powers of minus 1, right? And you'll get this plus minus pattern. So this first one will be, so you've got plus, minus, plus, minus, plus, minus, plus, minus, all the way to the nth term. And you know that you have a 0 because you've made x equal minus 1. So you know that your answer is 0 before you start. Right? Because 1 minus 1 to the power of n is just 0 to the power of n equals 0. Right? So just to reiterate, for 11D, we're saying x equals 1. For 12, we're doing the same thing. We're using 1 plus x to the n, and we're saying let x equal minus 1. Okay. So those ones I think are actually reasonably straightforward. Question 13 is more confusing. So in question 13, we're trying to show, we want to show that n choose 0 squared plus n choose 1 squared, etc., all the way up to n choose n squared, is 2n choose n. Okay? Now, firstly, they give you this hint. They say, well, consider 1 plus x to the n again, multiplied by 1 plus x to the n. You know that that would equal 1 plus x to the 2n. Why do you know that? Because you've got some base here, 1 plus x, multiplied by itself. So you've got a to the n all squared, which is a to the 2n, right? Where a is 1 plus x. So we know this is true, right? Okay. What would happen if we expanded? I want to start with the right-hand side, and I'm just expanding using my binomial theorem. We've got a formula for that. A n minus k, b to the k. All right, so we can set up this sum. if I was to do that on the right-hand side, the thing that's normally an n, well, that's now a 2n. So the sum is going to look a bit different. It's going to be 2n choose 0, 1 to the power of 2n minus 0, which is 2n, times x to the power of 0, plus 2n choose 1, etc., 1 to the power of 2n minus 1, x to the power of 1. In the middle, there's going to be a term, and I think it's in the answers. They give you the hint to look for this term, 2n minus. And by the way, all these powers of 1 to whatever power you like, it's just 1. At this point, you're going to get an x to the n term, right? And the coefficient for that term comes from 2n choose n, okay? We could keep going with this. We could have 2n, 2n minus 1, 1 to the 1, x to the 2n minus 1, and then the last term in this particular expansion, which I'm not actually interested in, this term, because I'm zeroing in on the x to the n term. That's the trick to this question. Okay. Right. Considering the left-hand side, similarly to what you were doing in question 10, right? If you had 1 plus x to the n times 1 plus x to the n, well, I'm just going to expand one of these 1 plus x to the n's for the meantime. We would get what? N choose 0. Now I'll have to write out a few. This is going to be a little bit annoying. N choose 1. 1 to the, I might just write out 4. N minus 1, x to the 1. Right. Obviously you've got potentially infinite terms here, depending on what your n is. N minus 1, just put the last two on. That's the 1, x to the n minus 1, and then your last term would be n choose n. 1 to the 0, x to the n, right? But all of this has to be times by itself, right? So I've just expanded one of these 1 plus x to the n's. Really what we've got is two of them. We've got n choose 0, 1 to the n, x to the 0, plus n choose 1, n minus 1, x to the 1. I'm not sure how many I can fit across the page. N choose 2, 1 minus n minus 2, x to the 2, plus dot, 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 plus. Let's see if I can get the last few in. N minus 2, 2, x to the n minus 2. I might run out of room at this point. N choose 1, 1 to the 1, x to the n minus 1. Yeah, I'm not going to fit everything I wanted to fit on here. N choose n, 1 to the 0, x to the n. But all of that is multiplied with itself, right? So I would have to write this whole thing out again. And I'm not going to fit it, so I'll just put the first term and the last term in, but you can see what I'm doing. Okay, so back to the key thing for this question is we've got, you know, a huge number of terms here potentially, depending on how high we want to go with our n's, and they've all got to be multiplied by every other term, you know, by every term again, if we were to square it. If we take all of these, like I've got to take this first term here, I've got to times it by every term there. Then I've got to take the second one, and I've got to times it by every term there. I've got to take the third one, I've got to times it by every. But what I'm going to do is only consider where you get an x to the power of n term. It's like, how are you making those? The first one's going to come from when this thing meets up with this one here, right? So you can hopefully see that we've got x to the 0 and we've got x to the n. And when they meet up with each other, right, so our x to the n terms, well, the first one would come when this meets this. N choose 0, 1. I think I might drop the 1s at this point. N choose n, x to the 0, and times by an x to the n. Right? Then we'll get another x to the n term when this term here, right, meets up with a term over here where it's an n minus 1 term, right? So I haven't written it here, I didn't have room. I've got it up here though. So when this term here, this n choose 1, 1 to whatever, you know, n minus 1 power, then I've got x to the 1. When that finally multiplies with this term here, n choose n minus 1, 1 to the power of 1, x to the n minus 1, I get another x to the n term. So I might write out a few of these. N choose 1 meets up with n choose n minus 1, x to the 1 times x to the n minus 1. And let's write out the next one. When an n choose 2, right, from this first expansion of 1 plus x to the n, when it meets up with an n choose n minus 2, right, we'll have x to the n minus 2 meeting up with an x squared. And I've written those in a different order. I'm not sure why I did that. Actually, that's confusing. Let's keep the order the same. X squared. So I'm looking at the x squared here meeting up with, oh, I didn't write it, but there's one in there. There's one in here that I haven't written, and it's an x to the n minus 2. Okay? But this potentially goes on forever. Well, depending on what your n was, right? But what we know is that at n choose 0, time is exactly the same. We know n choose 0 is 1, and n choose n is 1. So instead of writing n choose 0 times n choose n, why don't we just write n choose 0 squared x to the n? And then when we get here, right, n choose 1 is the same number as n choose n minus 1. This is coming from Pascal's triangle. So for example, if I went to the, maybe this row, 1, 4, 6, is this row 4 or row 5? I can't. Row 5, I think. Notice the symmetry, right? So this would be your n choose 1. In fact, let's write it out clearly. So we look at row 5 of Pascal's triangle. Goes 1, 4, 6, 4, 1. Right? And we've got 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. So what I'm really doing is I'm saying, instead of writing 4 choose 0 times 4 choose 4, let's just write 4 choose 0 squared. That's what I've done here. When we get to this one, let's just write n choose 1 squared x to the n. You can see this will make an x to the n term. That's like pairing up this 4 choose 1 with this 4 choose 3. They're both a number 4, they're the same number. When I get to the next, I'd have n choose 2 squared times another x to the n. So I'm not considering every single term, I'm just looking at the x to the n terms. Okay? I can then, now obviously that keeps going, but I can pull out x to the n and see what I'm left with, because every one of these terms has an x to the n in it. Let's pull it out and see what we're left with. N choose 0 squared plus n choose 1 squared, and this would go all the way up to n choose n squared. Okay? And that would be happening when your last term here, n choose n, multiplied with this term here, this first one, to make this last thing here, right? So this would all be some number, right? This n choose 0 squared plus n choose 1 squared plus etc., n choose 2 squared plus all the way to n choose n squared. We can equate the coefficient from this, right? We could therefore say that these two things in orange have to be the same, right? And what that means, so our conclusion up here, we could say that 2n choose n, this is giving the number part. This is just a power of 1, you know, don't care about that, it equals 1, right? This is x to the n. I'm just interested in the coefficient at the moment. That has to be the same as what's giving the coefficient here, which is n choose 0 squared plus n choose 1 squared. So this question is confusing because you need to know what to look for, right? But really the crux of it is do the expansions, but then we're zeroing in and we're just trying to consider the x to the n term from each expansion, right? Not the entire expansion, which potentially goes on forever. So I've written that down here. Only consider the x to the n term from each expansion, and you'll find that you've shown what you were meant to show, that these coefficients, you know, if you're looking at the coefficients that go with the x to the n term, from the left-hand side you get this series of squares, and on the right-hand side you would have to get 2n choose n.